can start whenever.
Okay. So today we are going to talk about neural networks. We're going to go through what a neural network is, why you need neural networks, how they function, what are some limitations to neural networks, and some buzzwordy phrases and what they actually mean. So what is a neural network? Well, it's a computing system or a modeling technique, much in the vein of linear regression or logistic regression. It's something where you can throw in your inputs and get a bunch of outputs. It's also a black box. Unlike linear regression and logistic regression, it's much harder to understand what is actually happening inside the neural networks, which means that it literally is you throwing your inputs at something and getting a bunch of outputs. It's much harder to interpret. We'll go over why. But first, why do you need a neural network? Well, we all know there is no phrase sexier than neural network. On any given day, a neural network is liable to get you a job, a spouse, and some certain strange circumstances, even a dog. But why do we really need a neural network? Because a neural network can solve certain problems that other modeling techniques just have a tough time with. Neural networks can deal with problems where you have a lot of input-output pairs. They can deal with huge amount of data because neural networks just learn better. They learn more like humans than any other modeling technique. You'd use a neural network if your data has a lot of errors. Let's say even 10% of your information has errors. Neural networks can just see through that and they're completely robust to noise. And you use a neural network when you want to apply your model to a new instance really quickly. That's why neural networks are used in things like automated cars, for example, because it can look at a new situation, a new combination of cars on the road that it has never seen before and just spit out an answer. Oh yeah, turn left. So, how does a neural network function? We're going to talk about four things. We're going to talk about the biological neural network, although I loathe to do so. We're going to talk about the perceptron. We're going to talk about many perceptrons coming together. And we're going to talk about training the network. Did I miss a slide? No, because the biological neural network is not important. The biological neural network is essentially built of neurons. And when you send enough electrical signals to a neuron, it fires off a binary signal. It does this a lot and it's very complicated. Now, the reason neural networks are called neural networks is because they were inspired by these biological neural networks. In fact, the first perceptrons, which is the neuron of an artificial neural network, the first perceptrons were built with the same functionality, using an activation function. If your inputs sum up to a certain point and fire off a binary output, otherwise don't bother. Now, newer perceptrons, more sophisticated perceptrons, are much more intricate than that. We're going to go through that. So the perceptron is the fundamental unit of the neural network. It is the powerhouse of the neural network. And it's actually very simple. Now, the beauty of perceptrons is that they are just functions. That's it. They're things where you shove in inputs and get a single output. Now, how does that work? Well, let's say you have your inputs. You have some raw bias number. You have input 1, input 2, all the way up to input m. You also have a bunch of weights. Now, what are you doing with these weights? You're applying them to the inputs. Let's say I have input 1 and a weight 5. I'm just going to combine the two and multiply them. So my combined input is now 5. So you have a bunch of these combined inputs times weights. And what are you doing with them? You're summing them. That's all you're doing. You're combining the inputs and then you're summing them. And then you're running them through an activation function. Now, what is an activation function? It can be absolutely anything. An activation function can literally be take everything at this point and add 1 to it. Now, naturally, certain activation functions are better than others. If I was just adding 1 to everything in a neural network, it would take a long time to train. So certain activation functions, stuff like ReLU, which is just a max of a number and 0, or a sigmoid function, which is what you'd use in logistical regression, or perhaps even a step function, which is what actual neurons do. Those are better functions than just adding 1 because they train faster. Now, the weights in a neural network are the only things that change. And how do they change? It's really very simple. let's say I shove in a bunch of inputs, I get an output, and my output is wrong. If it's lesser than it's supposed to be, I'm going to increase the weights. If it's more than it's supposed to be, I'm going to reduce the weights. That's all that's happening. And that's happening over and over and over again until we get to the right answer. So a single perceptron is actually a neural network on its own. It's just a very, very basic neural network. And back in the 40s and the 50s, this is the kind of stuff they were using, just single perceptrons. But then they realized that perceptrons have a lot of problems. A single perceptron can't even calculate the output of an XOR function, which is just really, really simple Boolean calculation. So a bit later, neural networks went in phases. They were popular in the 40s, then they were popular in the 80s, then they were popular in the 2000s. The second phase of neural networks was when they realized that, oh my god, you can just take a bunch of perceptrons and hook them up to each other. And that's when they started developing the first proper neural networks. And this is kind of what a neural network looks like today. You've got an input layer, you've got a hidden layer, and you've got an output layer. It's that simple. Okay? And when you apply the right activation functions and you keep running them over and over and over and over again, you are going to get the right weights for all your perceptrons. And this is going to lead to the right answers. Now, how do you train the network? Well, like I said, all you're doing is you're running inputs, getting outputs, and then you're reweighting the thing. That's all that's happening. Now, there needs to be some structure to this. So what we're going to do is we're going to take our training data, split it up into batches, and run multiple batches on the neural networks. Once a bunch of batches have been run together, this is called an epoch, we're going to reweight everything and then start running those same batches over and over again. Now, as you imagine, the more batches and the more epochs you run, the better your neural network is going to be. So, I'm going to answer a barrage of questions that I'm sure you have. Which activation function do you use? Like I said, any activation function will do the trick. You can add one, you can subtract one, you can literally just say input equals output and not do anything. But certain activation functions are better than others. And you pick them according to what you're trying to do. For example, in a logistic regression, chances are you want a sigmoid function. So if you're classifying data, chances are you want a sigmoid function. Similarly, for linear regression, chances are you want a linear calculating function. It's fairly straightforward, but these can make the difference between a good network and a bad network. Just figuring out which function you use in which layer is all there is to the art of building good neural networks. Now, how the weights change. The weighing system is very similar to what I described. If your answer is too low, you increase the weights. If it's too high, you reduce it. How it's actually done is using a process called stochastic gradient descent. And I assume Russell's going to cover that later this week. So I can answer questions on that later on if you have any. How do we deal with overfitting? Now, as I said, neural networks are extremely robust to noise. You run the same data over and over and over again to the point where it knows what's relevant and what isn't. That being said, there are ways to deal with overfitting. These include dropping out perceptrons, where a single perceptron will have very low significance to the entire model. And so you say, you know what, screw that, we don't want it. Another technique would involve just regularizing data as it's running through the network. Now, you must be wondering, it's fairly clear what a perceptron is doing, but what the devil is actually going on. And this is a slightly tricky intuition to grasp. So I'm going to try to illustrate what it does. Now, let's say you have a single perceptron, okay? I'm going to call that P1. And perceptrons are just functions, right? So let's say P1 is, and these are going to be functions of x. Let's say P1 is just beta naught, that's some weight, plus beta 1 times x. That's all that perceptron 1 is doing. And then perceptron 2 is just doing beta 2 times x and beta 3 times x. A neural network is just looking at those two and combining them. Now the keen observer is going to discern that what is actually going on is just beta naught plus x times beta 1 plus beta 2 times beta 3. And if we were trying to infer what a neural network was doing, that's all we'd be doing. We'd be taking a bunch of these little functions and just combining them and simplifying them. But it's a neural network, and neural networks aren't built for inference. So what we're going to do is just have a bunch of these functions lying around and just let them be. Shove in the inputs, get the outputs, and leave them be. But that is in essence what is happening in a neural network. We're just combining a lot of little functions. It's somewhat reminiscent of boosting, where you take a bunch of really dumb trees and put them together so that you have one complex tree that's actually really smart. So, what are some limitations of neural networks? Well, training takes a long time relative to other models. The reason neural networks suffered so many setbacks in the 80s, in what was called the AI winter, was because computers just couldn't handle it. In the 60s, they were using these titanic computers, these PDP-10s. They were literally the size of this corner of the room. And they had things like time sharing, where 8 people would use the computer at the same time. So it was really, really hard to run a neural network on that. And we've had processing problems with neural networks for a long time. In fact, it wasn't until the late 2000s and early 2010s that we started to fix them. Now we can run neural networks on multiple GPUs. We can run them in parallel, so they're actually processing extremely fast. But compared to other models, they are still extremely slow. Also, inference is a tad impossible. If you gave me, a pen and paper, 3 months, and maybe a PhD student, I might be able to do something with a neural network. But aside from that, you can only predict. It's fairly ridiculous to try to infer relationships from a neural network. So, this is the speed section of this presentation. Buzzword-y phrases and what do they mean? Okay, we're going to go through this one by one. Feed forward. This is a very simple one. It just means nothing ever goes back. Input goes here, output goes here, input goes here, output goes here. It's always going forward. That's what feed forward means. What's the next one? Let's see. Back propagation. Contrary to popular belief, this does not mean that anything is going back in the network itself. Back propagation means that errors are propagated backwards. So errors are calculated using stochastic gradient descent, and they're going to be calculated at the end of the neural network. So I look at the end, I look at the output, and I say, how wrong is this? I try to do some weight adjustment, and then I propagate that error backwards through the neural network. That's what back propagation is. It's just saying that the errors are propagated backwards. How about convolutional? Convolutional neural networks are essentially neural networks where a problem is broken down into specific patterns that the neural network can then simplify and understand. These are actually the next level of neural networks, and you guys aren't authorized to learn that in this class. I'm going to leave that for now. But let's move on to acyclic networks. Now, acyclic networks are actually what people are thinking of when they say back propagation. An acyclic network is just, you have a perceptron, you have another perceptron, and this goes to this goes to this, and woo, that goes back. That's what an acyclic network is. It's when something moves back. And these are actually, the acyclic qualities of these are seen in everywhere from hardware to basic Boolean logic. So it's not some amazing new concept. You've seen it in your if statements. And the universal approximation theorem. This is another fun one, because whenever any of your plebeian data scientist colleagues is using an SVM, you can just go to them and say, hey, have you ever heard the universal approximation theorem? Because the universal approximation theorem basically states that a 3-level neural network with a single hidden layer, so basically that can calculate any continuous function, can approximate any continuous function in the real domain. There are 2 caveats there. One is approximate. You can't calculate the exact function, but it can get pretty close. The other is continuous function, which means if you have a step function, something that goes like this, a neural network may not deal with that very well. But here's the other thing. You can approximate pretty well, and at some point, a continuous function can also approximate a discontinuous function pretty well. So neural network, despite all that they say about only being able to approximate, only being able to do continuous functions, can pretty much do everything. And what is dynamic modification? Dynamic modification is kind of what I was talking about earlier when I said you could regularize by dropping out perceptrons. That's what dynamic modification is. It says, let's take your neural network, which has the structure of a graph, and let's change the structure of the graph. We can add new perceptrons, we can drop out old ones. And that's all the buzzwordy phrases. Feel free to abuse them as you please. Any questions? Roland.
You mentioned before that it's really important to get your activation function right, and there were different activation functions that you might use for different models. But how do you know if you have a bad activation function or a good one?
So, like a lot of data science, you got to kind of do trial and error. Some things are a little clearer than others. For example, if you're trying to calculate a classification versus a linear regression, you would use at the end of your neural network a softmax function as opposed to a linear function. Similarly, a ReLU function can take place pretty much anywhere in the network and do an approximately good job no matter where you're using it. Also, another heuristic to follow is that if you're trying to do classification, then chances are you want a sigmoid or a tanh function somewhere in there. So there are these general heuristics that you can use, but at the end of the day, you probably just want to try stuff out and see what works better and what works worse. Because you don't know what's happening in that complex network. So it may not work as you expect it to all the time, but chances are it should follow a few